In our previous lesson, we talked about gravity outside a planet. Today's lesson is going to be about gravity inside a planet. Basically, we'll look at the force of gravity inside the planet and also calculating potential energy inside the planet. In the simple model that we used to work with, the simple model replaces a planet with a single point with the same mass of the planet. This is part of Newton's shell theorem. Unfortunately, this simple model is invalid when the object that we're trying to find the force of is inside the planet's radius. So Newton's shell theorem starts out by saying that outside a spherical object, that's what we were working with before, the gravitational field is equivalent to the gravitational field, assuming that all the mass of the planet is concentrated in the center of the object. Inside a spherical hollow shell, the gravitational field, however, is zero. A corollary to this is that inside a solid sphere, the gravitational field is only dependent on the mass of the sphere within the location's radius. If you want more information on this, you should check with your calculus teacher. For example, if we're looking at the little point right on the edge of the outer core, we're only interested in the mass of the inner core and the mass of the outer core. All the mass in the mantle we can ignore. So we can now reduce this entire planet to just the mass at the center of the inner core and the outer core, with the radius set at roughly 3,486 kilometers. Let's do a sample problem. The average density of the Earth is roughly 5,540 kilograms per cubic meter. Assuming the density is uniform, what is the mass of the Earth at a distance r that is less than the radius of the Earth? Well, we know that density, rho, that's a rho, not a letter p, so rho is going to be mass divided by volume. Rearranging, we get mass is equal to the density rho times the volume. For a sphere, the volume of a sphere is 4/3 pi r cubed, or making the substitution 4/3 pi capital R cubed. Substituting that back into our equation, the mass of the Earth at a radius less than the radius of the Earth is 5,540 kilograms per cubic meters times 4/3 pi r cubed cubic meters, or it gives us about 2.3 E4 times r cubed. Continuing with that, let's assume now that the density is uniform. What is the force of gravity on a m kilogram object at a distance r less than r Earth? Force of gravity, Newton's universal gravity equation, force of gravity is equal to g mm over r squared, where the capital M is the mass of the planet and the second m is the same m in the m kilogram object. From the previous problem, we know that the mass of the Earth at a distance r less than the radius of the Earth is just going to be rho 4/3 pi r cubed m all over r squared. Simplifying that equation, we get that the force of gravity is equal to g rho 4/3 pi r m. Looking at this equation, we notice that the force of gravity is going to be linear with the radius. So as we go farther away from the center of the Earth, the force of gravity is going to increase linearly with the radius. Graphing this, we graph both the radius less than r and the distance as we move out to infinity. The force of gravity, as you can see, when we graph it, increases linearly until we get to the radius of the planet, and then it decreases with r squared. So once we go away from the radius of the planet, it is inversely proportional to r squared. Okay, and it approaches asymptotically 0 out at infinity. What about the potential energy? Okay, remember that the potential energy is the integral of the force. Okay, if we integrate force dot product with the distance, okay, a linear function is going to become a parabolic function, and the 1 over r squared becomes a hyperbolic function that approaches 0 at infinity. Don't forget also that the potential energy is going to be a negative value because force and distance are opposite directions. So in terms of force times distance times cosine theta, that cosine theta means it's going to be a negative. Okay?